Buenos días a todos. Es conocido que una de las cosas que más nos puede ayudar en nuestro trabajo académico es la manera en que nos vinculamos con nuestros pares, y pues hacemos siempre la lucha porque exista esa vinculación y que ellos conozcan lo que nosotros hacemos y a la vez nosotros conozcamos y aprendamos de lo que ellos hacen, ¿sí? En particular, para mí me da mucho gusto esta vez traer a una persona de una universidad y un país con las que previamente no habíamos en mi grupo tenido una relación de cooperación académica, que es en este caso la Universidad de Weimar en Alemania, que es un punto importante en la investigación que se puede hacer en ingeniería estructural y en particular en ingeniería sísmica riesgo. Y la otra, pues, el hecho de ser el país, ¿sí? En este caso, la coyuntura fue la posibilidad de tener un proyecto conjunto con la Universidad de Weimar, con una universidad alemana. Entonces, en esa búsqueda de ver quién o dónde era la mejor posibilidad de ligarnos, es que tuvimos el gusto y la suerte de estar en contacto con quien es hoy nuestro visitante, y nos aventuramos en esta propuesta de un proyecto de investigación conjunto. Entonces eso es algo que pues estamos muy contentos de que se haya concretado. Estamos esperando la parte administrativa, de evaluación, etcétera, etcétera, pero el espíritu de cooperación ya se arrancó. Entonces, en esta ocasión, para mí es un gran placer presentarles al profesor Lars Abrahamczyk. ¿Eh? Soy malo en ese idioma. Quien es un profesor joven de la Universidad de Weimar, responsable de muchas cosas importantes en esa universidad, en el centro de Alemania, y que nos va a hablar de un tema que es importante para nosotros, que es el título de su conferencia, y al que le hemos agregado algo que desgraciadamente no nos hemos metido aquí en este instituto, que es este cambio climático. ¿Qué tiene que ver con las estructuras y con las cargas y con lo que debemos de hacer como estructuristas ante el cambio climático? Entonces, esta charla creo que en ese sentido va a ser muy extensa en sus alcances. ¿Por qué? Porque va a tratar la parte que es conocida para nosotros todo el tiempo, ¿sí? Y algo en la que yo tenga conciencia, no nos hemos asomado en este instituto. Debo de aclarar que yo estoy metidísimo en eso, pero en otros países y en otras instancias. Pero que es muy importante y que creo que dado las características de lo que está pasando, en donde el centro de masas de nuestra atención se está moviendo de los efectos sísmicos a los efectos asociados a problemas hidrometeorológicos. Entonces, algo que debemos de empezar a visitar y empezar a tratar como ingenieros estructuristas, que creo todos los que estamos aquí somos. Entonces, le doy la bienvenida a Lars. Welcome to Mexico. Yeah. And the floor is yours. Yes. And, cualquier cosa que quieran preguntar en su momento, por favor. No estamos ni obligados a entender todo el inglés. Cualquier cosa que a ustedes se les escapa, hagamos esta reunión una reunión útil. Entonces, welcome.
Muchas gracias. Yeah, thank you for this kind introduction, and thank you for inviting me, for the chance to talk to you here and to start this interesting collaboration. I would like to take the chance to briefly introduce where I am coming from, and then to talk a little bit about two topics. One topic will be climate change and what are the responsibilities of us as structural engineers. And the second one will go in the direction of earthquake engineering, what we are doing at Bauhaus University. So everybody of you knows Bauhaus, yeah? But Bauhaus is not only an art school, yeah? It's not only architecture, yeah? Bauhaus is also very strong in structural engineering. And we have a faculty over there, which is not anymore only civil engineering. We have renamed us to civil and environmental engineering. So we are 6 institutes. We are almost 20 professors. We have corporations all over the world. And comparable to you, yeah, only around 1,000 students. Yeah, but we are rather small university, but more than just art. Yeah. So what are we doing? So we are doing research as well as teaching in digital engineering, sustainability, resources, material and construction, but we also go in the direction of natural hazards. So this is what we are standing for, what we are doing at Bauhaus University and the Faculty of Civil Engineering. So as some key aspects, so Bauhaus stands also something for experimenting. Yeah, so, but Bauhaus stands from our point of view for willingness to experiment, openness and creativity. So we try to combine this along our research and teaching. Yeah, so here just a brief look at what we are doing. Yeah, so we are using modern technologies, we are doing testing, yeah, we are in building physics. So whatever you can imagine, we are dealing with it. So in energy and environment, for example, but also very much in construction. And as a very brief information, we have principally 3 different bachelor degrees, which are held in German language only. And then we have some consecutive master studies programs. They are also, some of them are fully taught in German, but we also have 2 English language master courses. One is dealing with digital engineering, so this is on the bridge between informatics and engineering, and especially from informatics, from media informatics. And we have this master course, Natural Hazards and Risk in Structural Engineering, which addresses natural hazard in the sense of a structural engineer. Yeah, so you as a structural, or we as the structural engineer will deal a lot with natural hazards, but at the end we are still a structural engineer. So if you look a little bit more into this program, so we try to learn from experiments, yeah, because we are Bauhaus, yeah, so we do a lot of experiments in our facilities, yeah, doesn't matter which type of material, reinforced concrete, steel, timber, yeah, we have a lot of stuff for doing diagnostics, but we also do, we also go on vacation, not vacations, excursions, with our students to visit construction sites, yeah, to really learn from the practice. And also here we do it for reinforced concrete, steel, timber, bridges, yeah, whatever is in the vicinity, we try to visit together with our students. Yeah. Beside that, I already mentioned, we do some other kind of stuff, and typically this is offered in optional courses. And for example, sustainable construction, there's a recent activity in straw houses. We do a lot of things in modeling and simulation. Here you see in wind simulation on bridges. But as I mentioned, we also do a lot in the direction of natural hazards and the evaluation of our building stock. Yeah, so we do some project thesis. So we are part of the global teamwork project. We do structural design, bridge design, and this is, I think, quite common among the different universities. So if you want to get more about the study program, feel free to approach me, and then we can discuss this. I would highlight a little bit this. This is our Bauhaus Summer School. This is a 2-week summer course, which we always offer every year. Yeah, so that's a quite nice chance to get abroad and to get in contact with other people. Yeah, so this is an annual summer school always held in August. And 2 more slides about the master study program, natural hazards. Yeah, you might imagine why natural hazards in Germany. Yeah, because we have natural hazards as well. Might be not strong earthquakes, but we have flood events, we have storm events, but we also have a tradition to deal with earthquakes because we went into field to learn from the earthquake, and our target is not the German market, so we are addressing actually national, regional, and international students. And what we do is we actually try to cover the whole cycle of an resilience or recovery, or the process of a natural hazard. So we have to deal with aspects before an event, during the event, after event, and if you are after an event, you are again before an event. So that's always the cycle, and this is what we train our students in this study program. So just if you would like to know more, yeah, we can discuss it afterwards and give you a brief idea about what we are doing in Weimar as a small university with, from my point of view, quite powerful topics. So now I would like to talk about two things. So differently from the announcement, I will start with the climatic loads, and then I come to the damage prognosis, because the climatic loads is a little shorter one and hopefully also quite interesting for you. So what is the starting point? So I think everybody knows climate change is there. Yeah, I think this we don't have to discuss anymore. Yeah, so there are many people who have talked about that. But we ask ourselves, what does it cost to us as structural engineer? What do we might to change in our design practice? Yeah, and the starting point, of course, for the motivation is the increase of temperature. Yeah, what we have already seen, what is always discussed. Yeah, and of course, motivation is also some observations. This is quite locally. So in the last, I think it was 2017 or something like that, we had a very ice storm in Germany, which caused collapse of our power lines. Yeah, because at that day, so there was a lot of ice hang around the cables, and the cables get that heavy that the mass couldn't carry it anymore. Yeah, and that was due to a climate effect. On the other hand, you might see some storm events, and the upper one is also a heavy snow load on a roof, which caused the collapse. So that means there are effects which are structural relevant. Yeah? So, and what we did, we investigated two aspects. We had a project funded by the national or the federal state of Thuringia, and we investigated the structural integrity and the room climate. Room climate I will keep a little bit separate. I will just focus on the structural integrity. Yeah, and so we had to go into the analysis of the recent climate data and the predicted climate data or climate at all, and then to look into the design concepts, the design values, and at the end to look into the probabilities. Yeah? And similarly, we did it for the room climate, and let's go a little bit fast. Yeah, and so what is the methodology? So first of all, we look to the scenarios. I think the scenarios are also quite known nowadays, so because it was talked about a lot. Yeah, so depending how well we will perform in reducing CO2 production, we will be on the so-called representative concentration path. Yeah, these RCP scenarios, and so the 2.6 would be actually if we stop doing anything, so that we keep the climate as it is, and the red one is, of course, if we perform as we do this last 10 years, then we will explore or tremendously increase the CO2 concentration. And so that's the key question on which path we are. So, and I just read it yesterday, so this path is not possible anymore. We are definitely in one of these two. So because we are not fast enough. Okay, so this was the motivation. So now from the methodology, so what we did, so we looked at the global climate models, yeah, which are done by this climate people, yeah, so they produce this kind of global models where you can see how the temperature will increase over the whole world, and then you see areas which gets really increase in temperature, but the question was, what does it mean locally? So that means we came from the global model, we had to study the regional model, yeah, so we took out of the global model this regional models, so this is also still done by the climate people, and then we looked to some climate station in our federal state, yeah, so that's Thuringia where we are in Germany, so that's just a small piece out of Germany, and to take the global model to the regional model to bring it on the local point, yeah, and then to investigate it more. Yeah. And for that, there's one step in between. So you see, typically you look to the historical data, and then you add, yeah, or you put to the historical data, you add the simulated data. Yeah. And the same thing, at the same time, you can compare this with the measured data. Yeah. So that means we did, or the people from climate, they do some historical simulation and they do some prediction simulation, yeah, so to look into the future, yeah. And beside that, you have the real measured data, and so this doesn't fit perfectly or not at all, and that's why you have to do a so-called bias correction. Yeah, so you have to adjust this so that you be in the same line. So beside that, we developed a little, for research purposes, 2 stations, so to measure our own data, and that we can derive the proper data. So, but what is now the methodology? And I think that's a little bit interesting. So because we have the climate data, yeah, we have the raw climate projection, we have the observation, we do the bias corrected climate projection, and then we have to do the extreme value analysis. Yeah. Because what happens now is that the climate isn't steady anymore. Yeah? So due to the climate change, we can't actually look into the past because the physics has changed. Yeah? So, and that's actually the key problem, why we have to do some extreme value analysis, yeah, to make some predictions, because at the end of the day, if you this part here changes, yeah, from the probability, and this is actually the part which defines our design values, yeah, or the characteristic values which we take into consideration to design structures, yeah. And because the extremes change, yeah, the tail in our probability distribution changes, and this is what we have studied here. And we compared this for the German standards with respect to temperature, wind, and snow. And therefore, what we did, we took the 2 climate projections, the RCP 2.6 scenario and the 8.5 scenario, and there are a couple of climate models. Yeah, there is not only one model. Yeah, so there are many, and at the end you have to study all to see what might be the final result. At the end, you still are in a range how this weather might become in the near future. Yeah. So, and then you have to aggregate the data. Yeah. So you look into here you see different. So one scenario with mean, min, and maximum. Yeah. And then you are along that. You have your observation, and this you have to compile and to do some analysis. And for the extreme value analysis, there we have actually in the past, we used the stationary approach, yeah, where we say, okay, that what happens in we take a time window of 50 years, yeah, and look into the probabilities for this data set. And in the past, we could say the equation is 0.98, or this 2% probability, yeah, and this for the stationary approach, yeah, assuming that it was the same over the last year, yeah. But now it changes, yeah, and then actually you can't go with a stationary approach anymore. You have to go in a non-stationary approach, And typically you take then time windows, of 30 years, 30 to 40 years, which you look at, and then you shift this into the future to calculate your probabilities. And if you are doing that, then you can come up with some probabilities, and you can look at, for the given probability according to your code, how things might change. And here we see, for example, the snow load. Of course, due to climate change, we increase the temperature, so the snow load probably decreases. But that's not always the case. There are also some scenarios where it still increases. So that's what you see here. So the green one would be the scenario that we manage our climate, and the red one is the worst scenario. And of course, for the worst scenario, we have an increase in the temperature and a decrease in the snow load. For our particular region. So at the end, this is very addressed to that what we have on the local side. Of course, there will be regions in the world which gets colder. And then you have to adapt this for this particular region. So if you look to the wind speed, wind is also quite uncertain, I would say, because here you see not that much differences between the models. So this is something which is not well solved in the climate change models yet. So we couldn't identify really a trend. So if you look at, so it's something more or less straight, independent, also how much the temperature changes, in which scenario you are. So from the wind, we couldn't observe too much. The same if you are looking in the gust wind speed, there we also didn't found too much things. The problem here is that in the climate models, we actually don't see real storms. So what we observe, so what is classified as a storm is difficult to extract out of the climate models. So from that point of view, so the data doesn't help us too much. But of course, the most trend you see in temperature, but also temperature is something which might be relevant for design, not for every building, but for temperature prone structures, which have an expansion like bridges, for example. And there we could observe definitely a trend, how the temperature will change similarly to that what the others have predicted. But now, in the sense of the probabilistic approach to say, okay, how much it might be in the future relevant to our design concept. And now the problem which results out of that is actually, in the past, our design philosophy was looking into the past and taking the same into the future. So that means looking in the past, calculating a probability, 2% exceedance probability, we take it in the future as well. But now the temperature increases in the future, and it doesn't work anymore. And that leads actually to many distributions. So temperature, for a lifetime of 50 years, a building, so from 2051 to 2000, and if we go now into the non-stationary concept, we reach a temperature between 38.5 to 40.5 degrees. But the question is actually, how do we consider now our probability? So far we say 2% probability in 50 years, 0.02. So, but the question is now how to sum it up. And due to the fact that it's a non-stationary approach, we have actually different possibilities. And the possibilities is either to say, okay, we accept a certain time, or a certain temperature, which has an 100 or 1% probability, or a probability of 0, more or less, which is smaller than the 0.98, and then with increasing temperature, I come back here. So with increasing temperature, then we exceed our reference temperature. from time to time or every year more than 2 times. Yeah? But the question is, how do we see it over the whole lifetime of the building? Yeah? Do we accept in the future more often, yeah, increase of the temperature? Yeah? Because that's the probability concept, that we accept a certain time that our design value or characteristic value is exceeded. Yeah? Now we could say we don't accept it for a very long time, but at the end of the lifetime of the building, it will be accepted. Yeah? Or we say, very conservative, that the whole probability, yeah, should be still this 2 times. Yeah? And this is a philosophical question which we can't answer, yeah, because this is a community problem, how to deal with this increase in the future. So that means from our point of view, this should be studied much more, yeah, especially to the local situations, yeah, how the climate change affects our design, yeah, and how it will affect our existing building, because they are not designed for that. Yeah, they are designed for a certain temperature or a certain wind speed, which will be definitely exceeded in the near future. And not only once, might be twice, 3, 4 times. And then we are out of our design philosophy. Yeah. Okay, so this as a starting point to give you some ideas where you might can work on in the future as well, or what we have to deal with as structural engineers. So now I would like to come back to some challenges in the damage prognosis, and I should take this, yeah, for particular with respect to reinforced concrete structures, what we have worked on in the past and what is still in ongoing research in our department or my chair. Yeah. So as a starting point, I think this is also something which you are quite familiar with, and so this is the relation between hazard, vulnerability, and risk. Yeah? So hazard is the maximum probable value of seismic parameter. Yeah? So that describes the event. Vulnerability describes the how structures perform. Yeah? And risk is nothing else than the multiplication of hazard with vulnerability might be multiplied by loss, and you get a risk value. So this as a starting point. Yeah, as a motivation, of course, there are past events which always give some task to us that we have to deal with this topic and how to improve the structures. How can we determine the risk, yeah, to communicate it with the decision makers. Yeah, so and yeah, for example, this are some damages from the Amatrice earthquake in 2016. Yeah, where there are a lot of masonry buildings were damaged. These are some pictures from Turkey on the right side, and left should be Chile. Also masonry structures, but here there are, for example, 2 pictures from Albania, the Albania earthquake. And the interesting part over here is that we have a reinforced concrete frame structure, which is actually designed for earthquakes. So it followed the Eurocode design rules, but with an heavy damage of the infill wall, which caused nearly collapse of the building because it's not functional anymore. Yeah, and on the other side you have masonry structures, yeah, which are standing next to each other without any damage. Yeah, so and this is what we are dealing with. And therefore, our approach is coming from the observation, and observation is somehow brought together in the European macroseismic scale. Might some of you know it, others not. So the key aspects of the European macroseismic scale is actually that we are having a classification of the type of structures. So we are distinguishing masonry, reinforced concrete, steel, and so on. And we assign to each structure a so-called vulnerability class. Yeah? So this is the vulnerability class. And if we know that, then we can link the vulnerability class with the probable damage under a certain intensity. You will see this in a minute. Yeah? On the other side, you can do this also analytically, yeah? Or you can in different manners. It always depends on the number of data you have. So what do you know about the exposure? And now we don't talk about a single building, we are talking about the building stock. Yeah. So, and there is always the question what kind of data you know, and can you apply a certain taxonomy? And depending on the taxonomy which you apply, either you have directly structural type, then you can apply the empirical approach, yeah, based on the EMS 98, for example, yeah, where we assign a so-called vulnerability class. Alternatively, you can go with the analytical approach, where you have a fragility function. Both together, you can build up some scenarios, and depending on the number of data and how many building types you have, it gets more complex and the uncertainty increases, decreases. You can quantify, and the best is, of course, if you do both and compare it with each other, because there are some differences. Yeah? And at the end, you can interpret and visualize the results. Yeah? You can disseminate it. Yeah? And of course, the best would be if you have an observation from a recent event where you can validate all what you have done. But this is the most difficult part. So, but at the end, that could be the outcome. That's some results from a research project in the southern tip of Turkey, yeah, in the Antakya region, which was, 2 years ago, heavily damaged due to this heavy Turkish earthquake. But at the end, what you can communicate is for a certain intensity, what is the probable damage, within the city. Yeah, and of course, this is always summed up for a district. Yeah, so that's the average or the summary of the whole district, how it might be performed. And then you can clearly see that there are areas which are highly prone to damage in case of an intensity 10 earthquake, and what you can expect. So therefore, to do that, I already mentioned, you need a building taxonomy, or the typology. And therefore, nowadays, there are many of them. So they are rather simple and robust one. For example, the EMS or the Jesus. So there are quite limited numbers you have seen. The more sophisticated is from the World Housing Encyclopedia. And very sophisticated ones are, for example, by the global earthquake model. You will see it in a minute. And you could have a look to it. So they always use different construction material, load-bearing systems. So these are the classification criteria that are considered in these typologies. And here you see also how many types of they distinguish rather fast. This is the typology from the global earthquake model. And you see there are a lot of parameters you need to know to assign a certain type of structure, which you later use for predicting the damage. And here, as a last one, this is the Jesus, and this is the very small one, let's say, but a very robust one for the EMS 98. So I will come back to that in a minute. So, because now what's the aim of the European macroseismic scale? On one side, we have the building types. So we classify our buildings according to the main material or structural system. And then we assign to it a so-called vulnerability class. And now the question could be, why do I have to distinguish type of structures, or why I don't distinguish them? And the answer is, how do they behave under seismic action? If they behave quite similar, then we can consider them as the same vulnerability. And for example, if we have an unreinforced masonry with reinforced concrete floors, so it would be in the most likely vulnerability class would be in C. And if we are looking into an reinforced concrete frame with a low code or with no earthquake resistant design, so not following any design rules for earthquakes, it's also in a C. So that means if they are standing next to each other under an earthquake, they behave similar. So that's the idea, to look into the buildings from the observation points of view, how they perform under seismic action. So that means vulnerability express the differences in the way buildings respond to earthquake shaking. So if one building type performs better than the other, it can be said that it had a lower vulnerability, yeah, but it can be also affected and modified by the engineer directly. So that was the ranges which we have seen. Yeah? And then the nice thing is that this is actually linked to some damage description. Yeah, and that was the new aspect within the European macroseismic scale, that now they have been added, yeah, for independency of the observed intensity. Yeah, so for intensity 7, we have now the description for buildings, because at a certain intensity, it causes damage to buildings. So for low intensities, it's typically just felt by some people. Yeah, so that is how intensity is described. Lower intensities are typically described by how people have felt it or how furnitures or things have performed. Yeah, but if you have larger shaking effects, then we are looking to the structures, how the structures perform. Yeah, and so the origin of that was actually to say, let's use this to describe the intensity, yeah, and to distinguish it between the different earthquakes. Yeah? It was more to determine what intensity has been observed than rather to do a prediction, but it could be used also for a prediction later on. Yeah? And that means now we could say, if we have an intensity 7 earthquakes, that many buildings of vulnerability class A, which are, for example, adobe structures, will have a damage of grade 3, and a few of them will have damage grade 4. So damage grade 3 is moderate damage, damage grade 4 is partial collapse. You will see it in a minute. Yeah? And this is actually the nice thing. Yeah? And then they also added, yeah, some damage description. Yeah? So what does it mean, a damage grade 3? Yeah? In case of a reinforced concrete structure, means moderate structural damage and heavy non-structural damage. Yeah? So, and please try to keep this in mind, that we always distinguish one damage grade higher, yeah, for the non-structural elements than for the structural. So that was the principal idea of the European macroseismic scale. Yeah. So that means at the end, so for certain intensities, yeah, so intensity is slightly damaging, yeah, you have always this description, and then you can either use this to determine the intensity in this certain area, or to use this to make a prediction, yeah, for a certain intensity earthquake. Yeah? Yeah? And the same, we have also some description for masonry structures. Yeah? And this is what we have used, for example, in our case study in Turkey. Yeah? So based on the vulnerability classes, which we have assigned to each building, we can come up with a prognosis, yeah, using some intensity attenuation functions. So depending where you place your epicenter, if it's here or somewhere there, yeah, then you can determine on each, yeah, more or less location, what is the local intensity, yeah, and this you link with the vulnerability. Yeah? Quite straightforward. Yeah? And then you can get to such results. Yeah, if you have this, then you can also combine this with some casualty scenarios. So you're using the amount of damage to now calculate what are the probable casualties in case of such an event. Yeah? And here we had to distinguish between daytime and nighttime, because in daytime, yeah, most of the inhabitants which are living here are working somewhere, and in the night they are back home, and then, yeah, so the number of people might increase in these vulnerable buildings. So how to do that now? Yeah, so at the end of the day, if we want to do a vulnerability assessment, we have different strategies, but what we need is actually, we need the hazard, we need some information about the subsoil condition and the building stock, yeah, and then we can come up with some damage scenarios. Yeah, and depending on the methods you apply, typically we have a typology, yeah, to distinguish or to classify our building stock. We can use a vulnerability assessment or fragility functions. And the best is, of course, if we combine this with a survey, yeah, so that we don't rely just on statistical data, that we really use look into the building stock which you observe. Yeah? And now you could think about, yeah, either you assess building by building, doing a numerical analysis. Yeah, if you want to do it for Mexico City, Yeah, I'm not sure how long you will need, but probably it takes too long before the next earthquake will happen. Yeah, so that's why we need some other methods. Yeah, that means we should either go with a simple one or then to a very detailed one. Yeah, and this is what we did. Yeah, we did within this project a rather simple one. We looked into the building stock. So what we have done is we did a survey, yeah, between 2005 and 2007. Now it's a couple of years ago, and we went to the city and we assigned to each building certain parameters. And the parameters were derived from the European macroseismic scale to determine the vulnerability. Yeah? And this, what we need is we need the material, yeah. In that case, reinforced concrete. So we put an indice, number of stories, yeah, because the number of floors, they play a role in the vulnerability. Then what type of building it is, if it's residential or a commercial building, and if there are some particularities, like a soft story or others. Yeah? And so we went through the city and assigned this to every building. Yeah? And based on this data set, we could perform the results which you have already seen. Yeah? And at the end of the day, yeah, so we had this overview, and here you could see there is a large portion of reinforced concrete structures within the city. And if you now can link this with the construction period, yeah, so then you might have also an idea how well these reinforced concrete structures were designed. Yeah? Whereas in case of Antakya, it was a little bit difficult as we had to observe during this very devastating earthquakes. Yeah? Here are some examples, yeah, how the buildings look like and how we could classify them. Yeah, reinforced concrete structure is rather clear. Yeah, soft story is quite common or was quite common in this region, but also in the older type of buildings, you had an increase of the upper floors, yeah, and we called it in cantilevering upper story. And then we added in a parameter widely rampantly built, yeah, to consider that the floors are on different heights, that the buildings are, yeah, widely attached to each other, which are definitely not good in case of seismic event. Yeah, so then we, based on the data which we collected, we did this classification, and then you could, yeah, do some statistics, yeah, number of stories, yeah, construction period, yeah, and then do you have a composition of the vulnerability class. And then actually the interesting thing is this very difficult graph. I'm sorry for it, but at that time I couldn't find a better idea how to visualize it. What you can see is the variation, yeah, of the probable damage grades, yeah, for a certain intensity, yeah, and using different approaches. Yeah. So the first approach is LC1 and 2. Yeah, these are the dots. Yeah, is the most likely vulnerability. That was the circle in our vulnerability table. Yeah, and this LCV5 is the pessimistic approach. Yeah, here we said, okay, let's say that every building is one vulnerability more worse than what we have observed. And if you assign this and if you sum everything up, then you see the percentage of buildings, what is the probable damage, and this is how you can visualize it at the end. Yeah, and this is, we distinguish for masonry in reinforced concrete, and then you see that, for example, this most likely here, yeah, gets from damage grade 2 to damage grade 3 in case of a pessimistic approach. And that's the basis then to have different scenarios which you can discuss, yeah, what is the most recent one. The second one, what we did, yeah, I already mentioned, you can do it analytically. Yeah, you can use analytical functions, and these are typically provided as fragility function. That's nothing else than the probability of exceedance of a certain damage grade, yeah, related to the peak ground acceleration as the hazard parameter. Sometimes you can also use spectral acceleration or intensity, so it depends on the functions you use. So here, just exemplarily, yeah, we did this as well. We looked into the literature, what are the available functions for 5-story RC frame structures with infill walls. That was our taxonomy, our type of structure. And then we found, okay, there are a couple of functions. And on the on your left side, yeah, you see the probability of exceedance for the yielding steel, yeah, means a slight damage, yeah, so just cracks, yeah. Here you can see, okay, there is some variation, but how it is interpreted is if you have a peak ground acceleration of 0.2, yeah, then you jump to this curve, and the intersection tells us what is the probability or how many buildings will exceed this damage. Yeah? And then you can see, okay, under a 0.2 earthquake, yeah, so 80% of the buildings will have slight damage. Yeah? If you do this for collapse, you get into trouble. Yeah, so here you see there are 6 functions, yeah, which are actually predicting the structural collapse. Yeah? And now you can see, depending on the function which you use, you can have either 90% or 5%. Yeah? And that's actually the difficulty which we still face, which function should be applied to your building stock. And that's why what we try to do within this project is to study representative structures to come up with our own functions, yeah, which are suitable for this region, that we don't rely on others' research. And then the other thing is, again, a very difficult graph, but we compared now the analytical with the empirical, and what you can see here is actually, yeah, our empirical approach are these gray dots. Yeah, so they are in the range of damage grade 2 to 3, yeah, for an intensity 9 earthquake. Yeah, and if I use a peak ground acceleration of 0.4 g, depending on the functions which I use, yeah, I'm 1 or 2 degrees larger. So that means there is still a discrepancy between the empirical approach, which is based on observation, and the analytical ones, which still needs to be studied, or at least there is actually no plausible understanding where this difference comes from. Yeah, so quite often these analytical functions, yeah, overestimate the behavior. Yeah, so they are predicting too worse behavior than what is observed in reality. Yeah. Anyway, so this is what we are studying. Yeah, and keeping this in mind, yeah, so that we have this variation in the fragility function, especially for reinforced concrete structures. This brought us to another topic, and the topic is, what does it mean if I have different level of earthquake resistant design? Yeah, so now the question is, first of all, what is earthquake resistant design? So therefore, let's try to discuss this on the basis of the pushover curve or the seismic capacities. So typically is, if you run a pushover curve, yeah, you have a base shear versus displacement, and now you say, okay, my structure will face different damages, and some of them damages are acceptable and others not, yeah, depending on your design code. Yeah? But in case of an earthquake resistant design, that means earthquake resistant design means I follow the different standard, yeah, with a certain ductility factor, for example. Yeah? But that also means that I have an acceptable limit of damage. Yeah? I accept damage. That also means that my structure will be damaged in case of an earthquake. Yeah? Especially if I have a design earthquake, yeah, I will have damage. Yeah? So, and that's now the big question, how to deal with that in the damage prognosis or prediction in scenarios, because I have an acceptable damage. Yeah? And that's a big question, and especially towards the behavior of the structural elements and the non-structural elements. Yeah? And this is what we tried to study. Yeah? And yeah, coming back to the vulnerability class, yeah, so typically we say, okay, a frame without earthquake resistant design, so not following any code, yeah, I have a rather low vulnerability, yeah, so between B and C. If I follow a moderate level or a certain design code, then I get a much better performance. But that's just describing the vulnerability. That's not describing the probable damage, yeah? Because the damage can be more or less the same. Because I allow damage, Yeah? And that is actually the key question of our research. And this is actually also what we found in the Albania earthquake, that the frames performed quite well because they were designed for earthquake, but the infills failed. And now actually, if we look into the damage description of the European macroseismic scale, there was always 1 degree difference. Yeah, moderate damage in the structural system, heavy damage in the non-structural damage. But here we had actually slight damage in the structural system and collapse in the non-structural system. Yeah, and that's something which should be addressed in the future developments. Yeah? And on the other hand, if we looked also to the lessons which we could derive from the Taiwan earthquake, for example, yeah, so Taiwan is known as a very developed country in sense of earthquake-resistant design. Yeah, so what they have is actually also earthquake-resistant design structures, but might they have some vertical irregularity or irregularity in the floor plane, which possibly cause torsional response, and which cause then this damage. Yeah? So that means also this is a part which is rather difficult. And this is what my PhD student presented in the World Conference recently, and he addressed these different challenges. So there are many challenges with respect to that. Yeah? And one is, of course, how to look at the shares of buildings with earthquake-resistant design, because typically this information we don't have. Yeah, and then to look a little bit in the reliability of fragility functions and not addressing the others. Yeah, and if we are looking to the shares, yeah, so this is some from census data. Yeah, this is now from Taiwan, for example. Yeah, if we look here, that the reinforced concrete structure is a high portion of the building stock nowadays. So that's a quite relevant topic. Yeah, but the key question is, yeah, if we look a little bit closer to the building stock, yeah, so then the majority is built before 1980, yeah, and in 1982 there was this first standard introduced. So might be that didn't got in play at that time, so might be a little bit later. So might be these type of buildings are following. Yeah, in 1999 we had changes in the code after the Chichi earthquake, and then there were recent some updates, yeah, from time to time in the following years. But it means actually what we see here is we don't have that many buildings which are earthquake resistant designed, which really faced an earthquake, yeah, where we can learn something. Yeah, so that limits a little bit our database. Yeah, so and that's is then the question from this information to what we have. Yeah. What are the performance in the different intensity areas or sites, and which amount of damage did they face? And then, what is now the right vulnerability class? Yeah? Can we predict this vulnerability class based on this observation? Yeah, and that makes it a bit, or why it is worth to investigate. Yeah, and what's the problem? The problem is as well, on one hand, the observation, on the other hand, what is already available in the literature. And here, for example, a set of fragility functions which claim that they have considered earthquake-resistant design. That means they did some numerical studies, for reference structures to say, okay, we have considered a certain design level. And for example, there are different regions in the world. So with and the description also varies, which makes it again difficult, because some say, okay, I have a low code and a high code, whatever it means. Others say with earthquake-resistant design and without. Others take into consideration the ductility class, to say I have designed structures for ductility, low ductility class, medium ductility class, or high ductility class. And others have, for example, pre-code, moderate code, high code, to address a little bit the code generation. And this is where we need a proper systematic to derive a new definition for it. But at the end of the day, if you look into the fragility functions which exist, we face the same problem which we have shown from the beginning. Yeah. So now we have a certain intensity measure, and if we are looking, so yielding in collapse and low code and high code. Yeah. So what we actually would expect, so this is something which we would rather expect, yeah, so that we have a low collapse, yeah, for the high code structure. Yeah. So this is how it should look like. That is what we would like to see. Yeah. And on the other hand, yeah, increased ductility, yeah, so is also something which we would like to see. Yeah. But again, high ductility means that I have acceptable damage, yeah, and it might happen that I have damage earlier than in static design structures, yeah, because I allow this damage. Yeah. And that's the key questions if we can see this in different fragility functions, and unfortunately it doesn't. I'm not sure if I have this slide here, but this is what we are at the moment studying. Yeah, how is this actually tendency or trends which we should observe reflected in the fragility functions, or how we can add this to the fragility functions. Yeah, and here we did a comparison about the different code levels among Europe. Yeah, so as a kind of, yeah, to distinguish, yeah, the type of generation and when it was implied in the different regions over Europe. Yeah. And the question is, should this be extended by the level of seismic design? Yeah, that we say, okay, we have a basic seismic consideration, static force adaptation, capacity design principles, or displacement-based design. If this might be better suited to distinguish these type of structures. Okay, this brings me to the end. Yeah, so this was a kind of starting point for this further discussion. Yeah, how to handle earthquake-resistant design, and what might be possibilities to capture this problem better for our risk simulations. Yeah, so from conclusion point of view, I think I will not read it here. So this is something to summarize. Yeah, on one hand, climate change is definitely an issue, yeah, which we should take care of, and it's not solved yet from the structural engineering point of view, from my perspective. And on the other hand, if we're going in risk study or resilience studies, we need a proper understanding of the building stock, yeah, that we can come up with good models and reliable models to decrease the uncertainties in our models. Okay, now I did it too fast. Good. Thank you very much.
Thank you. Do you have any questions? Anything that you want to? Yeah, please.
You will get the microphone.
Professor Lars, vielen Dank für Ihre Präsentation. But when you define the vulnerability class of the buildings, it took my attention that you only take into account structural features, but not geotechnical features, as we do here in Mexico. It's really important for us to take into account the seismic zone based on the type of soil that we have. Don't you think that those features needs to be included to obtain more reasonable fragility curves or seismic risk estimations?
Very good question, and thank you. But so you have to differentiate between the empirical approach and the analytical approach. In the empirical approach, vulnerability describes the performance of the structure, and the soil is part of the hazard. Yeah, so that means the soil should be included in the hazard. Yeah, as an intensity increasing parameter, for example. Yeah, so it modifies the intensity. Yeah, so that's how it is done in the empirical approach. In the fragility functions point of view, that's different. Yeah, because if you derive a fragility function, yeah, you do a proper design of a structure. yeah, and varying then the seismic action, and always look into the performance. Yeah? And of course, now you have to, on one hand, you should add this in the hazard again, because now your time history is from the site which you are studying. Yeah? But on the other hand, you might consider it in the design of your structure, which is the standard design for the fragility, to derive the fragility curve by the soil factor. Yeah? And that's something where you also have to be careful not to mix it too much. Yeah? Because on one hand, you take it into consideration in the design, which is correct. Yeah? But for the fragility function point of view, yeah, then again, you need as an input, yeah, is it now the peak ground acceleration at the site? Yeah, and then it should have include the soil amplification as well.
Okay, thank you.
Thank you. ¿Otra pregunta de alguien? Doña Karen, ¿no tiene alguna pregunta? ¿Sí? Anímese.
Thank you. What do you think about the importance of the modeling about the non-structural elements? And for example, the floor element that it's a rigid diaphragm or a diaphragm with flexible diaphragm.
Yeah.
How important could be that part of the modeling to take care of the fragility curves and at the end of the loss assessment?
Well, here you also have to distinguish between the structural system. For example, in masonry structures, it's very important. Yeah. So for reinforced concrete structures, I think the how you model the slabs, it's not of that high importance, because in reinforced concrete structures we typically assume a rigid diaphragm. Yeah. Whereas if we are looking to the infill walls, they should be considered. Yeah, because the infill walls, they have a consequence on the performance of the structure. Either on one hand might be, so it depends how they are built from the stiffness point of view and the dynamic response. If they are decoupled, then not, but they play an influence in the probable damage. Yeah, and what we have seen from Albania, so the structural system performed well, but the building is not usable anymore, yeah, because of the failure of the infill walls. So from that point of view, they are highly relevant.
Thank you.
Gracias. No sé si había preguntas en las personas que están conectadas en la red. Allá quien nos esté ayudando, no hay preguntas. Bueno, claramente creo que no tenemos más preguntas. Bueno, no, solamente me queda, we just have to thank you very much for your lecture, and we appreciate very much all the effort you took to come to Mexico and to meet people, and we had more than 20 people connected online. Yeah, so I think I'm sure you'll have an impact on whatever you hear from your lecture. Thank you very much once again, and we have a little recognition to your visit, which is a diploma that's signed from Our Lady Director, and this is for you.
Thank you very much.
And a little souvenir from this institute. Yes.
Muchas gracias.
All right. And por ustedes, pues están libres de en cualquier momento seguir platicando con él. Estaremos aquí un buen rato. Y muchas gracias por venir. Todos, buena tarde.